Hello sir, hello everyone. Myself Krishano Vishwas and today my discussion topic is pulse coded modulation. So at first we have to know what is pulse coded modulation. So pulse coded modulation is a modulation technique where digital signals we are converting to analog signal. It converts a continuous time signal into analog signal. So the basic process is at first we are doing sampling, then quantizing, and then at last we did encoding. So that's how PCM works. So why we what is the importance of PCM? So PCM is actually used in most digital telecommunication systems and along with audio CDs and we used everywhere. The core process of PCM, so I discussed that sampling, quantizing and encoding is the main process of PCM. So then we have basic block diagram of PCM generator. So in PCM generator there are three parts. First one is transmitter section, then channel, then third one is receiver section. So in transmitter section we have analog message signal. So at first we have the analog message signal. We pass the analog message signal through the low pass filter or LPF. So LPF actually did the low frequency uh, LPF cut off the high frequency and contain the low frequency. Then sampler did the continuous time signal, convert the continuous time signal into discrete time signal. Then quantizer actually did rounds of the values and then encoder. The signal is encoded by encoder. Then we have the channel, regenerative repetition to again regenerative repetition, and then we have the receiver section where we have uh, regeneration circuit, then what we have decoded, we have the decoder, we have encoded the signal, we have to decode the signal, so we have the decoder, then reconstruction filter, and then the destination. So this is actually receiver section. So we have the three main steps of PCM. The first step is sampling. So what is sampling actually? A continuous time signal may be completely represent in its samples and recovered back if the sample's frequency is Fs greater than Fm or equal to Fm. So where Fs is sampling frequency and Fm is maximum message frequency. So if the Fs, which is sampling frequency, is greater than the Fm, which is message frequency, maximum message frequency, then we can do sampling. So then, what is the purpose of sampling? Uh, converts continuous time continuous time analog signal into discrete time signal. So the purpose of sampling is basically converting the continuous time analog signal into discrete time signal. Then what is Nyquist rate? Nyquist rate actually is Fs, which is sampling frequency. In Nyquist rate, the Fs, the sampling frequency is have to greater than 2 FM maximum message frequency. Then here is the example for voice signal. Typically, sampling rate is 8 kilohertz. The bandwidth is 3.5 kilohertz. So this is actually the twice than the Fs. So here it is the example of Nyquist sample rate. So here we have the graph. In the first picture we have continuous time analog signal. Here we can see the continuous time analog signal. Then in the second picture we can see it converts into discrete time signal. So it is actually the discrete time signal here. And then and these two photos are actually this is the quantization levels. So I will discuss that later after completing quantization. So then the second important step of PCM is quantization. So what is quantization? Quantization actually. So quantization is a process of rounding of each sampled value of an analog signal to the nearest value within a finite set of discrete levels. So actually, each sample's amplitude is rounded off to the nearest value within the finite level. So here we can round off basically. Then there are two types of quantization: uniform quantizer and non-uniform quantizer. In uniform quantizer, we have two types. One is mid-rise quantizer and one is mid-rate quantizer. So, what is uniform quantizer? So, uniform quantizer is actually equal samples between levels. So, we have the equal sample between the level, and non-uniform quantizer is actually level sampled variables. Then we have mid-trade and mid-rise quantizer in uniform quantizer. So what is mid-trade quantizer? Here levels are equally spaced but not at zero. And in mid-rise quantizer, it is increase the level at zero. Here we can see the graph also mid-rise quantizer and mid-trade quantizer. Then we have quantization error. So quantization is actually rounding off. So if we round off something, then we actually have error. So the difference between the actual and the quantized value is known as quantization error. Uh, then quantization noise. So this is actually called also quantization noise. So the step size uh, of quantization noise delta equal to 2xm by q. So where q is quantization level and xm is maximum amplitude, and maximum error would be modulus in between modulus delta by 2. Then uniform distribution of noise. Here we can see a graph where the bandwidth is from minus delta by 2 to delta by 2, and the amplitude is 1 by delta. So variance of E is actually 1 by delta equal to minus delta by 2 E greater than equal to greater than equal to delta by 2 or 0 otherwise. Here mean is 0. We can see delta by 2 minus delta by 2 and delta by 2. So mean is 0. So we can calculate variance of noise. So this is delta square by 12, and noise normalized noise power is P noise equal to delta square by 12 if the R, which is resistance, equal to 0. Then we have signal to quantization noise power ratio, or SQNR. So SQNR equal to signal power divided by quantization noise power. So signal power is represented by P, and quantization noise power is delta square by 12. So here from here we can uh, calculate SQNR is equal to 3PQ square by XM square. Uh, and if we put Q equal to 2V, 2 to the power V, then we have 3P into 2 to the power V by XM square. Then normalized input voltage equal to xm equal to 1, if then SQNR is equal to 3p into 2 to the power v. Assuming p less than equal to 1, SQNR So then we have P is closer to 0, or so we have SQNR greater than equal to 3.3 into 2 to the power 2V. Uh, then we can calculate SQNR in dV is 4.8 plus 6V. Then the last step of pulse coded modulation is encoding. So encoding is the process of converting each quantized value into the its corresponding binary code for digital transmission. So it actually converts into binary codes. So here we can see the whole process. The analog signal we have actually we have at first sampling it, and then quantizing it, and then encoded it, and at last we have the digital data. So, application of PCM. We are use PCM in a very broader way. So, in telecommunication, we actually use PCM. In audio application, we use PCM. Modulation system, we can use PCM. In IoT device, 5G communication, we use PCM. And here some are emerging application, high resolution audio, or we know it as high res audio. uh, our headphone contains that, so where we can use the PCM actually. Then advantages of PCM. So at first we have high noise immunity, regenerative repeats possibility, multiplexing possibility, uh, multiplexing flexibility, and the disadvantage of PCM, it actually required high bandwidth and complex circuit also. And here we can also quantization error uh, we can face, and at least the at last it is high cost also. So that's it from my side. Hope you like my presentation. Myself Krishanu Viswas signing off.